and welcome to lecture 5 of module 3. What I am going to do now is, so far we have been talking of Gauss elimination method in terms of examples. What I am going to do now really is to take a look at an n equation in n unknown problem and then try to see what is the amount of effort that is required in terms of the number of steps the number of flops or number of floating point operations that will be required in order to to solve the problem using the Gauss elimination method. Okay. So again the problem that we have is going to be Ax equal to b, and then the first step that we will do is we create a matrix by catenating the columns of the vector b with the matrix A. Okay. We will consider an n by n size matrix A. So this is an n dimensional problem. Okay. And we will, although we have discussed about partial pivoting earlier, we are not going to consider partial pivoting at all in this particular discussion, simply because partial pivoting, the way computer is going to do partial pivoting is it is not going to do any kind of a computation, but it is only going to reassign the locations of the particular rows in its storage spaces. So it is very efficient when we want to do exchange of rows using for doing the partial pivoting. It does not take any computational any significant computational effort to do that. However, it takes fair amount of effort to do mathematical operations of addition, subtraction, multiplication and division. The older computers would do addition, subtraction much faster than they could do multiplication and divisions. As a result, historically people have been calculating the number of multiplication division steps and number of addition subtraction steps required independently. However, the new computers they are as efficient in doing multiplication division steps as they are in doing the addition subtraction step. So for newer computers the amount of effort required for addition subtraction is approximately similar to that required in multiplication division, one single instance of multiplication and division. So let us look at the A B matrix, and the A B matrix is going to be A11, A12, A13 and so on up to A1n, B1, A21, A22, A23, A2n, B2, A31, A32, A33, A3n, B3 and so on up to AN1, AN2, AN3 and so on up to ANN, Bn. Okay. In step 1, okay, A11 is the pivot element and R1 is the pivot row. We will use R1 to make coefficients in the pivot column equal to 0. Okay. So if we will do row operations in order to make A21, A31 and AN1 equal to 0, right, and how we do that is R2 we will replace it with R2 plus alpha 21 R1, R3 with alpha R3 plus alpha 31 R1 and so on, or in general Rj will be replaced with Rj plus alpha J1 R1, okay, where alpha 21 is nothing but A21 divided by A11. Okay. So now let us look at doing the first operation. Okay. So when we are doing the first operation, the row 1 remains the same, there is no change in row 1. So I will write it as A11, A12, A13 and so on up to A1n B1. Okay. The first computation is in computing A21. Okay. So, I will write the addition subtraction steps over here, multiplication division steps over here. Okay. There is one multiplication division step, that multiplication division step is to compute this particular coefficient alpha 21. Okay. So, now once we have computed alpha 21, we will subtract R2 minus alpha 21 into R1. Okay. As we had said earlier, we will not going to do this one extra calculation because we know a priori that this number is going to be equal to 0. So, this calculation we are not going to do. Okay. Here what this particular element is going to be, it is going to be A22 minus A22 plus alpha 21 multiplied by A12. Okay. So, this is one multiplication step and this is one addition step. Okay. So, there is one multiplication and one addition step in getting from A22 to A22 superscript 1. So, we will get this as A22 superscript 1 when we have one addition and one multiplication step. Okay. Likewise, A231 is going to be nothing but A23 plus alpha 21 A13. So, this is one multiplication step and one addition step. So, A231 is also obtained from one addition plus one multiplication step. Okay. And we repeat this for the remaining n minus 1 elements of the matrix A and one element of the vector B. Keep in mind that this distance, this number is n plus 1. Okay. There are n columns because of matrix A and n plus 1th column because of the vector B. This computation we are not doing explicitly, we are only doing all these computations. Okay. So, in this particular row operation we have the number of addition subtraction steps are going to be equal to n, the number of multiplication division steps are going to be equal to n. Okay. So, for row operation to get row number 2, the total number of multiplication division steps are going to be n plus 1, the plus 1 is for computation of that coefficient. Okay. So, this is the row operation in order to get row number 2. Now, let us see what happens in computing row number 3. In row number 3 again we get 0 over here. Okay. And we will compute A321 and again A321 is going to be equal to A32 plus alpha 21 multiplied by A12. Okay. So, this is what A31 multiplied by alpha 12. So, we need one computation again in computing alpha 31, okay, which is nothing but A31 divided by A11. Okay. So, that is one multiplication and division steps, and then to get A321 we will have one multiplication step and one addition step. Here we will have one multiplication, one addition step, so on and so forth, exactly in the same manner as we had it for row number 2. Okay. So, the number of steps required over here are going to be n addition subtraction steps and n addition multiplication division step plus one more multiplication and division step to get alpha 31. Okay. And as you see, what pattern we are following is that for each and every row the number of steps that are required are exactly the same. Okay. As a result of this, what we will get is a n2 1 so on up to a n3 1 a nn 1 bn 1 b2 1 b a 2n 1 a 331 and so on up to A3n1 and B31. Okay. All these are obtained through n addition subtraction step and n plus 1 multiplication division steps. Okay. And let us see how many rows are there to do this row operation. There is 1, 2, 3, 4 and so on up to n minus 1 rows. The total number of rows are n. The first row is being unchanged, only the n minus 1 rows are being changed. So what we are going to have is n plus n plus n, n minus 1 times, and n plus 1, n plus 1, n plus 1, n minus 1 times. So the total number of addition subtraction steps is going to be n multiplied by n minus 1, okay, and the total number of multiplication division steps are going to be n plus 1 multiplied by n minus 1. Okay. This is at the end of step 1. Okay. Now we will go ahead and see what happens in step 2. Okay. In step 2, A22 is the pivot element. Okay. Okay. Keep in mind that when we write algorithm for Gauss elimination method, okay, we do not create separate matrices, separate A matrices at each step. That would be extremely inefficient to do. What we are going to do is, as I have written over here, as soon as this particular computation is done, the original number that we had over here A22 is going to be replaced by A221. So although I am showing the superscript 1 over here and so on, in the computer memory there is only one A B matrix that resides in the computer's memory, and that A B matrix keeps changing when every time you do any row operation. Okay. As a result, as soon as this particular operation is done, the old value has already been replaced by A22 superscript 1. The superscripts I am using just so that I am able to distinguish the original values from the newly computed values. For no other reasons I am using these superscript. Keep in mind that you will use the same A matrix in order to do all the row operations and all the column operations. The results will be stored in the same A matrix. Okay. So now let us say what happens at the end in step 2, sorry, not at the end but in step 2. Okay, we will have this matrix again, and then we have addition subtraction steps, multiplication division steps. Okay. Row 1 unchanged, row 2 unchanged, so I will just copy those rows as they are, A11, A12, A13 and so on, A1n, B1, 0, A221, A231 and so on up to A2n1, B21. Okay. The next step we are going to do is R3 is going to be replaced by R3 plus alpha 32 multiplied by R2. Okay. Now this step first requires computation of alpha 32. Alpha 32 is nothing but A32 divided by A22, negative of that we will again put superscript 1. Again this putting the superscript 1 is really optional, because from a computational point of view it is the same variable that is storing that particular number. So we have one multiplication division step come in over here, sorry, one multiplication division step come in row 3. Okay. Now because of this particular value being 0, okay, no matter what row operation we are going to do, this value or the A31 value is not going to change. So this A31 value, the 0 that we had over here, will remain 0, it is not going to change. We are not going to waste one operation in computing this particular value. Okay. Same thing as we had done before, this A32 value after the first row operation, after this row operation, because of the choice of alpha 32 is going to definitely become equal to 0. So those values are not going to change. So the unchanged value, again I am going to, over here I am going to just put them with the red color chalk. Okay. So these two values are not computed, we just keep this value unchanged and we just replace the original value over here with a value 0. Okay. This A33 is going to be equal to A331 plus alpha 32 multiplied by A231. Okay. So this again in the same manner as we have been doing before, this is how the computation goes, and this will have one multiplication step, one addition step. Okay. And as a result of one multiplication and one addition step, we will get this value as A332. So A332 has resulted from one multiplication plus one addition step. Okay. And so on we will go on up to A3n2 and B32. Okay. Again for computing A3n2 we will have one multiplication plus one addition step and one multiplication plus one addition step over here as well. Okay. Now there are total number of columns are n plus 1, and two of the columns we have not done any addition, subtraction, multiplication, division steps at all. None of the algebraic manipulations are done over here. We have kept this number as it is and we have replaced this original number with 0, which does not require any significant computational effort. As a result of this, the total amount of effort is going to be for n minus 2 multiplications and n minus 2 additions. There are n plus 1 columns, n plus 1 minus 2 is actually going to be n minus 1, sorry, not n minus 2. Okay. So we will have n minus 1 addition subtractions, n minus 1 multiplication divisions, and plus one more multiplication division to get alpha 32. So we will have the total number of operations is going to be equal to n. Okay. Then we will do this for row number 4. For row number 4 again we will have exactly as we had in this particular case, in this particular operation, step 2 operations. In the same way we will in the step 3 as well, these two numbers are going to be 0 and there will be one multiplication, one addition steps in the remaining n minus 1 computations. So as a result again we will have n minus 1 number of addition subtraction steps and n multiplication division steps in this particular row, and this will go on up to here. Okay. So the number of times we have this is the total number of rows are n, okay, and the rows that are changing are row number 3 to row number n. So that means n minus 2 rows these operations we are conducting. So the total number of operations that we get is n minus 2 multiplied by n minus 1, and in this particular case the total number of operations are going to be n multiplied by n minus 2. Okay. So in this case the total number of operations were n multiplied by n minus 1 and n plus 1 multiplied by n minus 1. In this particular example we have n minus 2 multiplied by n minus 1 and n multiplied by n minus 2 operations. Okay. And we will continue this so on and so forth for n minus 1 steps total, and we will, so in the next step we will have n minus 3 multiplied by n minus 2 operations of addition subtraction and n minus 1 multiplied by n minus 2 of multiplication divisions. So on and so forth. So total number of addition subtraction steps are going to be equal to, okay, we go back over here, n multiplied by n minus 1, then n minus 2 multiplied by n minus 1, n minus 3 multiplied by n minus 2, and so on and so forth. So n minus 1, n minus 1, n minus 2, n minus 2, n minus 3 and so on. This is in step 1, step 2 and so on up to step n minus 1, and in step n minus 1 we will have 2 multiplied by 1 number of steps. Total number of multiplication and division steps the total number of multiplication and division steps are going to be n plus 1 multiplied by n minus 1, n multiplied by n minus 2, so on and so forth. Okay. So, this as a result what we are going to get is the total number of addition subtraction step is just sum of these, and the total number of multiplication division steps is just sum of this particular thing. So, in other words, the total number of addition subtraction steps are going to be summation I multiplied by I minus 1, where I goes from 2 to n, okay, because we have n minus the total number of steps are n minus 1, as a result this goes from 2 to n. 2 to n is going to be the total number is going to be n minus 1, okay, and this we can write this as summation say k equal to 1 to n minus 1. So, we have k where k is going to be just I minus 2, right, sorry I minus 1. So, this we can write this as I minus 1 multiplied by I minus 2, where k sorry I multiply I plus 1 multiplied by I, or k plus 1 multiplied by k. Yeah. So, from k going from 1 to n plus 1, and this is going to be equal to summation of k plus k square, okay, summation k equal to 1 to n minus 1 of k is going to, it is nothing but 1 plus 2 plus 3 up to n minus 1. If we have up to n, the result is going to be n multiplied by n plus 1 divided by 2. If we have up to n minus 1, is going to be half of n minus 1 multiplied by n, okay, and summation of k square is from k equal to 1 to n minus 1 is going to be equal to 1 by 6 multiplied by k minus 1, sorry n minus 1 multiplied by n multiplied by 2 times n minus 1 minus plus 1, 2 times n minus 1 plus 1, and that is going to be 2n minus 2 plus 1, 2n minus 1. Okay, which we can write this as n square minus n by 2 plus 2n cubed. So, n minus 1 2n minus 1 is going to be 2n squared minus 3n plus 1 multiplied by n is going to be 2n cubed minus 3n squared plus n divided by 6. Okay. So, these are going to be the number of addition subtraction steps. Okay. If these are the number of addition subtraction steps that we have, the leading term over here, so let us say if n is very large, say n is moderately large, say n is 10, even if n is 10, n cubed is one whole order of magnitude larger than n squared and 2 orders of magnitude larger than n. So, as the number of elements start increasing or the number of variables start increasing, n cubed starts becoming larger much faster than n squared or n. As a result, the total amount of effort required is actually governed by this particular term. So, the number of addition subtraction steps or effort in terms of the total number of addition subtraction steps is of the order of n cube divided by 3 in case of Gauss elimination method. Okay. And the total number of multiplication division step is n minus 1 n plus 1 multiplied by n minus 1 n multiplied by n minus 2 and so on and so forth, which we will be able to write it as summation I equal to 1 to n minus 1 and this is I multiplied by I minus 2. Okay. So, or sorry, I multiplied by I plus 2. So, at 1 it is going to be 1 multiplied by 2. So, 1 multiplied by 2 plus 2 multiplied by 4 plus 3 multiplied by 5, so on and so forth, up to n minus 1 multiplied by n plus 1. So, this we can expand this as summation I equal to 1 to n minus 1 I squared plus 2 times summation I equal to 1 to n minus 1 2 I, sorry 2 and this. Okay. And this summation of I squared is the same as summation of this I squared. So, again the order of effort is going to be determined by summation of I squared, where I goes from 1 to n minus 1. So, for multiplication division steps also effort is of the order of n cube by 3. So, in summary, what we have for Gauss elimination method is that the amount of effort required in solving a problem Ax equal to b scales as the cube, okay, not square, not linearly, but as the cube of the number of variables n. So, when we start with an equation Ax equal to b, where x is an n dimensional vectors and we have n equations, if we were to use the Gauss elimination method, the amount of effort is going to be of the order of 2 n cubed divided by 3, because we have n cubed divided by 3 as the multiplication division steps and n cubed divided by 3 as the addition subtraction steps, sorry subtraction. Okay. So, that is the effort involved in Gauss elimination. In exactly the same manner, we can also compute the effort involved in back substitution, and if we were to do that, we will find out that the back substitution step scales as n squared and not as n cubed. Whenever we have any problem of the sort Ax equal to b, we can employ the methods such as Gauss elimination to solve a general problem. What we just saw a few minutes back is that Gauss elimination is highly computationally intensive method. It is computationally intensive because the number of computation required for Gauss elimination are proportional to n to the power 3, okay, where n is the number of variables in the vector x that we are solving for. So, for example, if n equal to 10, we have the number of computations that are required in order to use Gauss elimination are of the order of 1000. Okay. However, from n equal to 10 we go to a slightly larger problem with say n equal to say 100. This particular, the number of computations that are required increases from 1000 to 1 million, and that is because Gauss elimination scales as n to the power 3. Now, if from n equal to 100, if we go to n equal to 1000, the amount of computation required is going to be 10 to the power 9. So, as we increase the number of equations that we are solving, the amount of effort required in Gauss elimination increases very rapidly. Okay. Now, for a general purpose problem Ax equal to b, we do not have a choice because Gauss elimination turns out to be one of the more efficient ways of solving a general purpose problem Ax equal to b. However, a lot of problems of interest to engineers, chemical engineers, mechanical engineers and so on, are not a general purpose problem. They have a specific structure, okay, and they have a structure what is known as a banded structure or a sparse structure. Okay. So this matrix A is not a full matrix, but it has a certain type of structure, and where does that structure comes from, I will come to that in a couple of minutes. But because it has a certain structure, there are certain properties of that structure that we can actually exploit, and that is exploited in some of the more efficient ways of solving. Those are banded solvers, as they are called. A specific example that we are going to take of the banded solver today is called the tridiagonal matrix algorithm. Okay. And a tridiagonal matrix algorithm is applicable to what are known as tridiagonal matrices. So let me come to what tridiagonal matrices really are and how these tridiagonal matrices come into existence for a typical problem that we see in chemical engineering. Okay. So the tridiagonal matrix structure is of the form. So this is what we have, the matrix A is going to be. In the tridiagonal structure, the diagonal elements of the matrix may be non-zero. One more set of elements just below the diagonal may be non-zero. One more set of elements just above the diagonal may be non-zero, whereas rest all the elements in this matrix are going to be 0. An example of this could be, for example, you can have a matrix say A11, A12, 0, 0 and so on up to 0, A21, A22, A23, 0 and rest everything else is going to be 0. Now this particular guy is two locations of the diagonal, therefore this guy is going to be 0. Then we will have A32, A33, A34 and rest everything will be 0 and so on. We will have 0, 0, 0, 0 and so on up to ANN, and there will be over here this term is going to be A n minus 1 comma n, rest everything in this particular row is going to be 0. So this is a tridiagonal structure. As we can see over here, this particular diagonal may be non-zero, this super diagonal element may be non-zero and this sub-diagonal elements may be non-zero. Everything else in this structure is zeros. Okay. So again this is called a diagonal, this is what is known as a super diagonal, and this is going to be sub-diagonal. Okay. And if we have one diagonal element, one super and one sub-diagonal element, what we actually get is a tridiagonal matrix. Okay. And going further, taking this concept of tridiagonal further, we could basically also have a banded diagonal matrix or a banded matrix. Okay, where there would be one diagonal element and more than one super diagonal elements and more than one sub diagonal elements. So for example, there might be two super diagonal elements, two sub diagonal elements and rest everything else might be 0. Now these are special structures because we know a priori that everything over here is going to be 0 and everything over here is going to be 0. The computational load for this can be reduced quite significantly compared to a general Gauss elimination method. Okay. So if we were to solve problem Ax equal to B, where A has a tridiagonal structure, okay, then we can use the TDMA method, tridiagonal matrix algorithm, as I had said earlier. We can use this TDMA method to reduce the amount of effort from n to the power 3 to n to the power 1, and I will show that in a few minutes. Okay. Okay, it is common in lot of engineering problems. Okay, especially when we are going to express a model for an engineering problem in terms of a differential equation. Okay, we will come to this in more details in module 7, module 8 and module 9 of this particular lecture series. Let us consider a rod that is losing heat to the surroundings, and let the surroundings be at 25 degrees Celsius. One end of the rod, let us say, is heated and kept at say 100 degrees Celsius, and let us say the other end of the rod is kept at 25 degrees Celsius, and we want to find out how the temperature varies in this particular rod. Now this is a straightforward engineering problem which results in what is known as ordinary differential equations boundary value problem, and under steady state this equation ends up being 0 equal to k d square t by dx square minus h a multiplied by t minus 25 equal to 0. Okay, so this is the conduction term and this is the heat loss term that comes over here. Now what we can rewrite this entire problem as d square t by dx squared equal to h a by k t minus 25. Okay, so this is going to be the overall differential equation where one end of the rod is kept at 100 Celsius, the other end of the rod is kept at 25 degrees Celsius. Okay, and when we rewrite this particular equation, what we are going to do is we are going to discretize this particular rod in multiple segments, and we can discretize this in n minus 1 segments. Okay, and when we do that, we will result, what we will get is we will get n equations in n unknowns, and those equations, and I am not going to derive them right now, but I am just going to state them very quickly. We will do the derivation in module 8 of this particular course, module 8 lecture 2 onwards we will take that derivation. Our T1, that is temperature at the first end, is going to be equal to 100. Okay, for our second segment we are going to use basically this equation, and we are going to expand it using the numerical using the derivatives definition at this particular location. So if this location is location 2, then d square t by dx square is going to be t3 minus 2t2 plus t1 divided by this, let us call this as delta x, so divided by delta x squared. Okay, so what we will have is we will have t3 minus 2t2 plus t1 divided by delta x squared is going to be equal to h a divided by k multiplied by t2 minus 25. Okay, and I take delta x squared on to the other side, I will be I will basically get t3 minus 2t2 plus t1 equal to h a delta x squared by k t2 minus 25. Let us call this guy as alpha. Okay, so we will get this as alpha t2 minus alpha multiplied by 25, let us call 25 alpha as nothing but beta, so where beta equal to 25 alpha. Okay, So this is what we will get. We will rearrange this, we will take T2 onto, or rather we will take beta onto the other side, and these guys we will take onto the right hand side, and we will get beta is going to be equal to minus T1 plus 2 plus alpha T2 minus T3 is going to be equal to beta. Okay. So this is what we are going to get when we redo this particular procedure for the third element. We are going to get beta equal to minus T2 plus 2 plus alpha T3 minus T4 equal to this left hand side, so on and so forth, or we will get beta equal to minus T I minus 1 plus 2 plus alpha times Ti minus Ti plus 1. Okay. So now our overall structure of our A matrix is going to be determined as follows. Let us define X equal to nothing but T1, T2 and so on up to Tn. Okay. Then our equations can be written in the form like this. So the first equation is T1 equal to 100, or it is going to be 1 0 0 and so on up to 0 multiplied by T1, T2 and so on up to Tn equal to 100. Okay. Our second equation is going to be minus 1 2 plus alpha minus 1 and rest everything is going to be 0. So it is going to be minus 1 2 plus alpha. I will just rewrite this so that there is enough space for me to write everything. Okay, 2 plus alpha minus 1 and rest everything is going to be 0, and over here we will have 0 minus 1 2 plus alpha minus 1 and then everything is going to be 0, and this will follow in the subdiagonal element, this will follow in the diagonal element, this will follow in the super diagonal element, everything else will be zeros over here, and the last equation is going to be Tn equal to 30 Tn equal to 25, which is going to be just this 1 multiplied by Tm equal to 25, and all these guys are going to be populated by the left hand side, which is going to be beta and so on. Okay. So this is going to be the overall structure. Our A matrix has the tridiagonal structure. The tridiagonal structure, if we come and look over here, this was what the tridiagonal structure was. Okay. So we have the diagonal element, the super diagonal element and the subdiagonal element. All the diagonal elements are 2 plus alpha except for A11 and ANN. All the super diagonal elements are going to be equal to minus 1 except the first guy. Okay. All the subdiagonal elements are again going to be minus 1 except the last guy, which is 0. Okay. So this is a tridiagonal matrix structure that comes in because of the heat conduction problem. Similar tridiagonal structures you will get from a plug flow reactor problem or a fixed bed reactor problem or a membrane problem, where we are going to, if we were to model say reverse osmosis process in a membrane, we will get a similar type of model and so on and so forth. So we are going to get tridiagonal matrix type of structures in a lot of problems of interest to chemical engineers. We are going to cover them in module 8 in much more details and how to get to this tridiagonal structure. Now the first step in Thomas algorithm is going to be to make this particular element, this pivot element, equal to 1 by dividing the entire row by that particular element. So we will write step 1. The first part is divide R1 by A11. Okay. That is what we are going to do. The next step in case of Gauss elimination was to use the pivot element, or sorry, not the pivot element but the pivot row. So, to use the pivot row R1 to get zeros in C1 below the diagonal. Okay. So, this was the second step, the second part of step 1 in Gauss elimination. Now, let us go and look at what kind of structure we have in the tridiagonal matrix. Okay. Now, in the tridiagonal matrix, row 2 has a non-zero element, row 3 does not have a non-zero element, row 4 does not have a non-zero element up to row n. None of these rows have non-zero elements in their column 1 below the diagonal, only one row has non-zero element. Okay. That is the first thing to keep in mind. The second thing to keep in mind is that in row 1 this particular element is going to be non-zero, this element is 0. So, this guy minus anything multiplied by this guy is going to remain this minus anything multiplied by this is going to remain this, and so on and so forth. So, for wherever I am marking this x marks, we are not going to need to do any calculations at all. Okay. And we will need to do one more calculation over here. Okay. So, what it means, in order to use the pivot row, we will use the row R1 to get 0 in this particular element. That is the only thing that that is needed, and once we get 0 in this particular element, the only element that is going to change is A22 and B2. None of the other elements are going to change at all. So, what we are going to do over here is we are going to rewrite this, use pivot row R1 to convert A21 equal to 0. Okay. That we are going to do by writing R2 equal to R2 minus A21 multiplied by R1. Okay. And unlike Gauss elimination, okay, there are not going to be n steps in this, there are only going to be 2 steps. Why there are 2 steps? Because only 2 elements are non-zero, A12 and B1, these are the only non-zero elements. Okay. Because of this, what we are going to have is A22 new is going to be equal to A22 old minus A21 multiplied by A12 new. Okay. This is going to be one equation, and the other equation is going to be B2 is going to be equal to B2 old minus A21 multiplied by B1 old. Okay. So, these are the only 2 equations or only 2 expressions that we are going to actually solve for when we are going to use R1 in order to get the pivot element, the elements in the pivot column equal to 0. So, what does that amount to? Okay. So, what that amounts to is this guy, when we divide throughout by A11 becomes equal to 1, A12 becomes equal to this guy is going to be A12 divided by A11, which we will write A121 okay, and B1 becomes B11. Okay. So, this involves one division and the second division. So, step 1 involves 2 divisions. The first part involves 2 divisions. What we do next is this particular row minus A21 multiplied by this row. By doing that, this particular element gets converted into 0. We know it is going to get converted into 0, so this computation is not done. A22 is going to be equal to, as we had seen earlier, if we look at this equation, A22 is going to be A22 minus this particular product. So, there is one multiplication and one addition subtraction step. So, that is going to convert A22 into A221. Okay. A221 is nothing but A22 minus A21, which was the old value over here, multiplied by A121. Okay. None of these numbers change, these numbers remain as they are, and B2 gets changed to B21, and again using the equation that I had shown earlier. B21, remember, is nothing but B2 minus A21 multiplied by B1, which involves one addition subtraction and one multiplication division step. This involves one addition subtraction plus one multiplication division step. So we have two additions and two multiplication division steps. Okay. So step 1 involves 2 addition subtraction steps plus 4 multiplication division steps in step 1. Next, what is going to be step 2? Our step 2 is going to use this particular row as the pivot row. So in step 2, row 2 becomes the pivot row. Now let us look at what happens in step 2. Okay. So in step 1, row 1 was the pivot row. Instead of that, in step 2, row 2 is the pivot row and A221 is the pivot element. Okay. Now we are going to use the pivot row. Instead of R1, we will use the pivot row R2 to convert not A21 equal to 0 but A32 equal to 0. Okay. And this is going to change appropriately. Now again let us go back and look at what that is going to involve. Okay. We are going to use this particular row, okay, to get zeros in this particular column, in this particular column below the diagonal. Okay. So if this is the diagonal, we need to get 0 over here and everything else below that is 0. So the only computation that we are going to do is for row 3. There is no computation that will be done for row 4, row 5 up to row n. Likewise, this A32 itself on its own is going to become 0 because we are going to we are going to subtract from R3 this particular row appropriately. Okay. So this on its own is going to become 0. A33 will change because this is a non-zero element. Okay. And A332 is going to be nothing but A33 minus A32 multiplied by A23, exactly the step that we did over here. A similar step will be done over here. A34 does not change because the guy over here is 0, rest everything is 0, so none of these values change, and the only other value that changes is B3 becomes B32. Okay. This also requires one division step to convert this into 1. By dividing, this gets converted into 1, this gets converted into A231 or sorry A232, and this gets converted into B22, where B22 is nothing but B21 divided by A221. Okay. So there is one division and 2. There are 2 division steps exactly as we had earlier. There is going to be one addition subtraction and one multiplication division step to get this guy. There will be one addition subtraction and one multiplication division step to get this guy. So 2 addition subtraction plus 2 multiplication divisions plus 2 multiplication divisions over here. So as before, we will have 2 addition subtraction and 4 multiplication division steps in step number 2 as well. Okay. And we are going to keep doing that for n minus 1 rows, just as we did in the Gauss elimination step, and that each of these steps is going to require 2 addition subtraction plus 4 multiplication division steps. So total computational requirement is going to be n minus 1 multiplied by 2 plus n minus 1 multiplied by 4. These are the addition subtraction steps and these are the multiplication division steps. Okay. And this is exactly where the Thomas algorithm or the tridiagonal matrix algorithm has an advantage over the Gauss elimination, that instead of this method being n to the power 3 computational, this method having an n to the power 3 computational requirements, has n to the power 1 computational requirements. So when we go from n equal to 10 to n equal to 100, the number of computations required are going to go from order of 10, that means perhaps it is going to be 6 multiplied by 9, so 9 times 6 is 54, so it is going to go from 54 computations to 540 computations if we are going to use 100 steps. Okay. So the amount of increase in effort with the increase in total number of n, when we are discretizing this type of a boundary, the amount of increase in effort is manageable when we are going to use a method such as a tridiagonal matrix algorithm. Okay. So with that I will come to end of this particular lecture, lecture 5 of module 3. What we basically covered in lecture 5 of module 3 is the Gauss elimination and tridiagonal matrix algorithm, and we compared the two by looking at the amount of computation required for each step, and therefore we looked at the total computational requirement for both the Gauss elimination and the tridiagonal matrix algorithm.